Before we resume the linear algebra lesson from last time, I want to point out a few Prismia updates, some of which I think are going to be really cool. So for one thing, we have a completely new drawing tool. I don't know how much you used the previous one, but it was pretty mediocre and I've been wanting to improve it for a long time. And we have that now. So the previous one worked just like a painting canvas. So whatever you draw onto it, it changes the pixels and that's it. It doesn't remember the geometric structure of whatever you drew. And this one does. So it can handle vector graphics and you can go back and move things around after you add more stuff to it, which I think is pretty essential if you want to do anything serious with a drawing tool. But the more important reason that I put this in is that it enables a real-time whiteboard. So this means that I can draw on my whiteboard in my classroom view and the figure updates directly in your chat window. So let me try that out and see, just check that it works. I'm pulling up my whiteboard and turn on the freehand tool and start writing. And here I'm just writing with my finger, but you can see that it updates in real time in your window. So that way I can draw without having to screen share some other thing that's like screencasting my iPad or whatever. Okay, so this point is just to save some time setting up whiteboarding through Zoom and to keep you from having to switch back and forth. And also it commits these handwritten notes to the class transcript. So it saves some time on the part of the instructor, not having to necessarily prepare everything. In the lesson, you can plan a few spots where you can write everything out by hand. I don't expect to take advantage of that part too much, but other instructors might want to. Yes, this real-time whiteboarding thing, it's dependent on having this new whiteboarding or this new drawing tool in place. And that happened just recently. Another improvement that I made is that I can now see a dashboard showing your Mathlet or your drawing tool or your code cell or your text box. So whichever thing you updated last, that's what I see. So if you start playing with this Mathlet here, then I can just pull up my dashboard and see what everybody's doing with it. And the other thing that I added to the Mathlets is this little camera button, which you can click to put a copy of the Mathlet into your window here. So it doesn't do everything. The text is rendered in a way that makes it very difficult to insert here. So you're just going to see the graphics objects. But in most cases, I think that's totally fine. And that way you can sort of record kind of the end state of however you manipulated the graphic rather than it just being ephemeral where, you know, whatever you did, you lose it later. And also it pops up in your drawing tool as well. So you can, I guess, let me delete everything and then put that back. So you can put this into your drawing tool if you want to sort of like add something else to it, you know, say like, hey, look at this part right here. By the way, I can't grab this thing because it's behind. So what I do is kick this back and now I can grab this arrow and move it around and be like, you know, look at this part of the graph right here. And then I can click insert to put that into my chat window and send it, but I won't. I'll just delete everything here. Okay, so I just wanted to show you around a little bit of some of the tools that are available that are new. Yeah, so let's go ahead and get into the actual content for today. So last time we concluded just as we introduced the term rank for the dimension of the range of a linear transformation. Let's start with a geometric view here. In the figure, I want you to move the images of the standard basis vectors. So remember, you can control where the standard basis vectors go, and that controls the entry of the matrix. And I want you to just do it in such a way that the resulting matrix has rank 1. We're seeing a variety of different answers here. Let me go ahead and share a few of them. So we have a couple folks. Okay, we have the green and purple vectors aligning in the sort of northeast direction here. We have these aligning in the east direction. A lot of folks just chose due east. That's fine. I'll give you one with a little bit of a different direction, but the point is they need to be either aligned or anti-aligned. So I could do it this way, want them exactly opposite each other like this. But the important thing is that both of them map to a single line. And the reason it's clear that needs to happen is that if A is supposed to have rank 1, then every input vector has to be mapped to a single line. So that's what it means to have rank 1. It means that the image of the whole input space is one-dimensional. In other words, it's just a line. And that means that both standard basis vectors have to map to that same line. So you just need to align them. That's the point. So this is the mental picture to have in your mind for a rank deficiency, specifically for a matrix from R2 to R2 or a transformation from R2 to R2. If things sort of fall along a single line, then it's going to be rank 1. And by the way, I added this slider here to help you visualize the transformation a little better, because as it stands without the slider, if it's just stuck here over at 1, which is the way I had these figures before, you can't really see dynamically how the transformation is operating, which makes certain things a little hard to observe. Like for instance, we'll put this back over here. You can see in this way, so the points are morphing from where they start to where they end after you apply the transformation. And you can see that this isn't an orthogonal projection. Like if you track where this point right here goes with your eye, it's not going to go orthogonally to the line. It's going to go upwards. And you can arrange the transformation to do all sorts of things. So the points move for a rank 1 transformation. They'll move towards this line, but not necessarily at a 90-degree angle. It might be, whatever angle, depending on, exactly how the transformation works. So here you can get the points to sort of move up and to the right as they go towards their final spot. Okay, so here's another one with the same thing. So you want to just use this same figure up here. So what does a rank 0 matrix look like? The only zero-dimensional vector space is the one containing only the 0 vector. So that means we need both of these points to be at the origin. So we'll squish both things down here. Everything gets collapsed to the origin. That's not perfect. So what I can do is zoom in, get them closer. There we go. And then zoom back out. By the way, I'm holding shift to make this zoom and pan stuff work. So you have to be on desktop for that, but everything squishes down to the origin. That is a rank 0 transformation. Okay, so in these two exercises, we just did rank 1 and rank 0. We didn't do rank 2. I didn't ask you to show me a rank 2 matrix. Why is that the case? All right, so some good answers there. So folks phrased it in several different ways, but it's very much the same idea. So rank 2 is kind of almost anything. So if you just grab the green and purple arrowheads here and just do whatever random stuff with them, all of these are rank 2 transformations. We had to do something very special, namely getting them all on a line or putting them both at the origin to get rank 1 or rank 0, but you don't have to do anything special at all to get a rank 2 transformation. So all of this stuff is rank 2. So the point is that a rank deficiency is what's notable. It requires a sort of conspiracy among the columns to commit linear dependence. So they have to sort of get together and be like, you know what, let's be on the same plane or the same line when we don't have to be. And that's what's interesting. So being full rank or having the maximum possible rank is easy to do. It's what you get when you just throw vectors down at random. So one thing I want to comment on here is it maybe feels like we haven't changed directions, actually. The mathlets that we're looking at, there is this plane on the left side so that there's an understanding that we're talking about a transformation. But at the same time, we could just focus on the right side and think about when do two vectors span a plane, when do they span a line? Those are ideas we've already talked about, right? And what we might conclude here is that for them to span the whole space, they need to be linearly independent. If we have two vectors and we want them to span a line, they need to be linearly dependent, etc. So in this sense, the idea of a matrix rank is really just repackaging the idea of span. We're just putting it into the sort of language of a linear transformation, but really we're talking about the span of some columns. And I want you to think specifically about why that's the case. This is an important idea to get down because it comes up a lot when we're thinking about linear algebra. So why is it the case that the rank of a matrix is equal to the dimension of the span of its columns? So we didn't define it that way. We defined the rank of a matrix to be the dimension of its range as a linear transformation. And now we're saying that's the same as just the dimension of the span of its columns. Why is that the case? All right. A few answers came in. I'll ask Nick to talk about his answer. Great answer. So this is exactly what's going on. So I highlight this question because, as I said, it's a really important fundamental concept, and it takes a few times of recognizing that that's what's showing up here to internalize it. So this is one such instance for you. Both of these quantities, the rank of the matrix and the dimension of the span of the columns, are measuring the same thing. And the reason is that if you want to talk about an arbitrary linear combination of the columns of A, you can write that as AX, where X is an arbitrary vector. And that's because the definition of the matrix vector product says, take the linear combination of the columns of the matrix with weights given by the entries of the vector. So this is just a tidy repackaging of the idea of all the linear combinations of the columns of A. But then we also have a term for this, A times X, where X can be whatever. That's also known as the range of the transformation that maps X to AX. So the dimension of the range of the matrix and the dimension of the span of its columns are the same thing. All right, here's another question. What's the rank of this matrix? So I just want you to look at it. I designed it to be computable by inspection. So you should be able to read off the rank by examining that matrix. Yeah, so it's rank 2. And the reason is that the first two columns are not parallel. So you can just look at that and see, like, what would you need to multiply this one to get this one? Well, it'd have to be 1 for these entries to match up, but the rest of the entries don't match. So these two are not parallel. But then if you look at this one, it's just twice that one. So this is linearly redundant. It's already in the span of these first two. So the span of the first two columns is going to be the range of the transformation. And just to drive home this point above, what we were saying about the equivalence of the range and the span of the columns is that we can write the set of all linear combinations of these 3 columns like this, where we put an x1, an x2, and an x3 here as factors to multiply these 3 columns by. And we get, in this way, the range of the matrix as we let x1, x2, and x3 vary over all real numbers, or all triples of real numbers. And we also get the span of the columns. Again, that's just the definition of the matrix vector product. So I'm going to use this example to segue into the next topic, which is closely related to rank. It's the idea of null space. So the nullity of a matrix or a transformation is the number of dimensions worth of vectors that get mapped to the 0 vector. And the set of vectors which map to the 0 vector get a name that's called the null space. So maybe just to take a break from my script and come back to this picture to talk about the null space, if we go back to the 0 matrix that we talked about, so roughly the 0 matrix, everything maps to the origin. This is a matrix whose nullity is 2. All 2 dimensions worth of vectors in the input get mapped to the origin. If we look at our rank 1 matrix that we talked about, this takes a little more work to see, but there's going to be a whole, maybe let me move this one down here to make it just a little easier to see. There's going to be a whole line's worth of points that get mapped to the origin. So it's, in this case, it's going to be the vectors that point northwest, southeast. If you watch these corners of the grid, they're going to collapse in towards the origin. By the way, I should have had this at a higher zoom level. So the nullity of this transformation would be 1. And if you look at something that's ranked 2, then nothing maps to the origin other than the origin itself. Everything is 1-to-1 here. What if you know where a point maps to, you can just trace it back through this visualization to see where it started from. So this would have nullity 0. So geometrically, that's what's going on. All right, so back to the matrix picture. Name one vector in the null space of this matrix. The same matrix we just looked at. There is a, well, sorry, I should say name one non-zero vector in the null space. So there is a non-zero vector in the null space. If you can think about what it is. Okay, 0, 2, -1. These work. Other answers that folks suggested had positive entries. So the reason you can tell that a positive entry is not going to work is imagine multiplying this matrix by a matrix with three positive values here, and you carry out that matrix vector product. You're going to be multiplying positive values by positive values in every column and then adding up the results. So everything's positive. So there's no way to get to the 0 vector by just multiplying and adding purely positive stuff. So, but what's going on with this solution is, well, we noticed earlier that twice the middle vector is equal to the last vector. So if we give that middle vector a coefficient of 2, hit this with a 2, then it will match this one. And so if we hit that last one with a -1, then these will all become the opposites of these values. And when we add those two, we'll get zeros. And then we're multiplying that first column by 0. And so that wipes that out. And so everything ends up adding up to the 0 vector. So you can kind of see what's going on here. We can say that the observations about linear dependencies among the columns, those are equivalent to, I should say, non-zero elements of the null space. So the vector of all zeros will always be in the null space, because if you multiply 0 by every column, that wipes all the columns out. You add up all the results, you get 0. So that's not that interesting, but non-zero elements of the null space are in correspondence with observations about linear dependencies. In other words, again, coming back to the definition of the matrix vector product, an observation about a linear dependency takes the form, here are some weights you can use to linearly combine the columns to get the 0 vector. And those weights, by definition of the matrix vector product, give you an element of the null space. You just put them together into a vector and you have an element of the null space. Okay, so here's a question that you may have seen before, but we'll do it anyway. So consider the linear transformation which maps every point in the plane to just the nearest point on the line y = 2x. What's the nullity of that transformation? And what does the null space look like? I'll summarize what people said so you can see. Right, so there's several correct answers here. The dimension of the null space should be 1, and because there's a whole line of points that map to the origin, this is correct as well. Several folks were thinking like, well, what are the things that would map to the origin? Well, really would just be the origin, right? So that's not the case. We'll see there are a bunch of points which map to the origin. Right, so let's see a picture to kind of understand what's going on here, because I think most people pretty much have it, but there's some misconceptions. So here's the line y = 2x. If you take a vector like, I don't know, 1, 1, and you ask where it goes, it's going to map down to this point, the nearest point on the line y = 2x, which is not the origin. So this is not in the null space. But if you take a vector like this one here, that's on this orange line, and you say, okay, project this orthogonally to the nearest point on the teal line, well, that's going to be the origin. So all the points on this orange line get mapped to the origin. So let me see if I can illustrate that again with this figure. By the way, you can pin things in the classroom. It usually is not that great of an idea because they end up being big. You can also edit the message to kind of make it a little bit smaller. I'm probably just going to unpin this in a second. But if we map the green and purple vectors to the nearest point along the line y = 2x, I'm just going to eyeball that. Just squish it down, squish this one down. Something looking vaguely like that. Then here's what it looks like. So how everything along this line, if you kind of trace this point with your eye, it's going to map into the origin. And everything else is going to map somewhere else. Like if you watch where this point goes, it's going to go up here somewhere, so it's not going to go to the origin. So you have this whole line of points that maps to the origin. That's what's happening here. So I want to mention one other thing that, in a way, it's sort of not that interesting, but it also needs to be said or else you'll get confused. If we think about an m by n matrix and we think of it as a transformation from one Euclidean space to another, what are those two Euclidean spaces? What are the domain and the codomain of the transformation that maps a vector x to a times x? Sorry, I didn't put a timer on this one, but I do want you to try to answer. The domain is Rn and the codomain is Rm. And the key thing to remember here is that m and n get swapped around. So we say that A is an m by n matrix, yet it maps Rn to Rm. And the reason is just that this is how matrix multiplication works. So imagine we have 3 rows and 2 columns. So this is a 3 by 2 matrix. And you're like, okay, what can I multiply that by? Well, these are supposed to be weights for a linear combination of these 2 columns. So there have to be 2 of them. If there were any different number, it wouldn't match up. So the input here, the thing that we multiply on the right, it has to have a number of rows or a number of entries, which is equal to the matrix's number of columns. And likewise, what output do we get? Well, when we linearly combine all these columns, their lengths are going to be preserved. Nothing changes the lengths of the columns here. So if we have 3 rows to begin with, in other words, each column has length 3, then the output, the column will also have length 3. So on the output side, you have number of rows, and on the input side, you have number of columns. And that means that things get switched around. It's just an inevitable consequence of defining function application in a prefix rather than a postfix way. In other words, we could have chosen in the distant past to write this product as x times a, where the transformation would be applied on the right. And there's some things that would be nice about that, like if we applied multiple transformations, we'd be tacking them onto the right, and so they would appear in order. Like if you apply A and then B, it would be X, A, B, and that would be kind of nice because A and B are in the correct order. As it is, we have to do it the other way. It would be B, A, X if you want to apply A and then B. And then likewise, these things wouldn't get swapped around. But anyway, it is what it is at this point. Okay, so one thing that we've sort of hinted at in these visualizations that we've looked at is that if you want to introduce a rank deficiency, so if you want to introduce an unnecessary linear dependency among columns, you have to do that by mapping a whole extra dimensions worth of vectors to 0. So we looked at some examples in the plane where the rank is 2. In that case, the nullity was 1. We looked at some examples where the rank was 1. In that case, the nullity was also 1. And then we looked at rank 0 where the nullity is 2. So it seems like rank and nullity trade off against one another. To increase either by 1, you have to decrease the other by 1. So like, for example, suppose we have a list of 8 vectors in R13 and their span only has dimension 3. So what would be the nullity of the matrix obtained by assembling those 8 vectors as columns into a matrix? The nullity of this matrix would have to be 5. So the idea is like if there were no linear dependence among the vectors, the span would be 8 because you have 8 vectors if every one represents a fresh direction. But here the dimension is actually 3. So we lost 5 somehow. We had 5 separate linear redundancies, if you will. There's a whole 5-dimensional space worth of vectors that maps to 0. So the nullity is 5. So I want to look at this numerically. I want to suggest that we should have as many different some kind of mental handles on this as we can. And looking at this numerically is pretty powerful. So let's go ahead and start up our Python session. And what we have here is the randint function from NumPy's random module, which is just going to generate a matrix full of random integers. And we can specify the size 9 by 6, and we can specify the range that the values can be. So this is going to be -10 to 9 because upper bounds are exclusive in Python. And so this is saying take every row, the colon says grab them all, and the 4th column, so indexing from 0, and set that equal to the difference between the first 2 columns. And so this is this equal sign is an assignment operator. It's clobbering whatever was there before. So we populated this matrix with random stuff. but then it didn't matter what ended up in that index 4 column because we just replaced it with whatever we computed here just now. And then likewise, we replaced the 5th column with some particular combination of these first 2 columns. And then we're like, hey, what is that matrix? Show it to me. And so here's what we get. And if you know, like for example, 7 minus -1 is 8, sorry. I'll tell you, Python with the zero-based indexing, when it comes to matrices, it's confusing because we are so hardwired to compute matrix indices using one-based indexing. But in any case, you'll have like -6 minus -1 is -5 and so on. So that's what's going on here. What is the rank of A going to be when we compute it? So I'll show you how to compute it in a second, but just based on what you see here, what do you think it's going to be? Okay, so lots of folks got this right. Let's hear from Francis. I don't think we've heard from you yet. Great, that's exactly right. So these first 4 vectors were randomly populated. It is conceivable that one would be in the span of some other ones, like maybe this third one is actually some linear combination of the first 2 or whatever. That's extremely unlikely. If you're just grabbing random directions, it's very unlikely that you're going to happen to fall on the lower dimensional space that has already been spanned by some initial random vectors. But then these last 2 vectors are definitely going to be linearly redundant with respect to the first 4. So once we get to this one, by design, it was in the span of, in fact, just the first 2, and this one is in the span of the first 4. So these last 2 are going to add nothing. So the rank is just going to be 4. The range is going to be equal to the span of these first 4 linearly independent vectors. So that's the punchline. Rank 4 is by far the most likely outcome here. We know it can't be more than 4 because we introduced those linear dependencies ourselves. Conceivably it could be lower, but that's extremely unlikely. So the way you want to check this is using the matrix rank function from numpy.linalg. So this is a function you import from numpy.linalg, and you just compute it. And sure enough, it's rank 4. Okay, what will the dimension of the null space be? Right, so the null space would be just the 0 vector if the matrix had rank 6. That's what it would be if we hadn't introduced these 2 linear dependencies here. But since we introduced 2 linear dependencies, we're going to get 2 dimensions worth of vectors mapping to 0. And in fact, I didn't make a message about this, but you can say what they are just by looking at these combinations. Like, we can say that 1, -1, -0, 0, 1, 0 is in the null space. And that's because I'm using this index 1 to pick out the 4th column, and I'm saying, oh, sorry, this should be like that. And I'm saying that if I subtract 1 of the first column and add 1 of the second column, as well as 1 of the 5th column, then I'll get the 0 vector. So that's just by design. And then likewise here, I can say 0, -1, -0, 3, 0, 1. So this should be -3 as well. So these 2 vectors are linearly independent, and they're both in the null space. So the null space will be 2-dimensional. In fact, it'll be spanned by these 2 vectors. And again, that's just coming from the coefficients of this linear dependency that we created when we ran this line of code. We can check this, by the way. So you do have to get this from SciPy instead of NumPy. But in any case, there is a null space function, and we can compute the null space of A, and it tells us indeed that it's 2-dimensional. So if we ask for the shape here, it'll say it has 6 rows, of course, because that's the dimension that it has to be something that you can multiply A by. But then it has 2 columns indicating that there are 2 dimensions in this null space. So these 2 vectors are the ones that this particular computational routine has picked out as spanning the null space for this matrix A. There are lots of other choices that you could make, of course, for a set of vectors that spans a given 2-dimensional vector space. These are a couple. Okay, so that worked out. Here's a question related to the above that again, it's maybe not super interesting, but it's worth thinking through because it comes up and you want to have thought of it before. What's the maximum possible rank of a 14 by 20 matrix? All right, so we had two answers here, 20 and 14. So that makes sense. It's better be one of these two numbers. So let's think about what it's asking. So it's saying, what's the maximum possible dimension of a vector space spanned by 20 vectors in R14? So each of these columns is going to be a length 14 vector, and there are 20 of them. Well, think about the lower dimensional case. What if it gave you 5 vectors in R3? So the first 3 could be linearly independent, and then they would span R3. But then the 4th one and the 5th one would have to be linearly redundant. You've run out of space. You've already spanned the entire 3-dimensional space with the first 3 vectors. You will definitely be able to get the last 2 as a linear combination of those first 3. So the maximum dimension would be 3. Same thing with R14 and R20. Once you get 14 vectors, if it is linearly independent, you've already filled up the space. And so the remaining 6 vectors are not going to do anything for you in terms of increasing the span. Okay, let's flip it around. What's the maximum possible rank of a 20 by 14 matrix? The important thing here is it's a completely different question, really. It's saying that you have 14 columns in R20. Now you have plenty of space. You have 20 dimensions that your vectors are sitting in. You have 14 of them. So best case scenarios, they're linearly independent, and in that case, they'll span a 14-dimensional space. So 14 is the maximum here. So we can say that a matrix is full rank, meaning that its rank is as big as possible, given the shape of the matrix, if its rank is equal to the smaller of its number of rows or number of columns. And a matrix which is not full rank, we'll say is rank deficient. And we're 2 minutes over time, so I'll stop it there.